Hello everyone, welcome to the presentation of the physics projects that are proposed by the Laboratory of Advanced Semiconductors for Photonics and Electronics for the next academic year. My name is Raphael Butte and I am a senior scientist at LASPE. So we have four main physics projects to consider. The first one is dealing with the investigation of the optical properties of near-surface 3-nitride quantum wells. The motivation behind this project deals with the novel optoelectronic applications that would be based on the interplay between 2D materials and 3-nitride semiconductors. 2D materials are very much studied nowadays and they can be freely controlled. We mostly consider the following families of 2D materials: hexagonal boron nitrides, perovskites, transition metal, dichalcogenides, and black phosphorus. So all those materials are characterized by different bond gaps, and the idea would consist in depositing a flake of such 2D materials on top of bulk 3-nitride semiconductors. 3-nitrides are direct band gap semiconductors that can cover a wide tunable range from the deep UV with aluminum nitride down to the near infrared. So our experiments would consist in depositing a flake of 2D materials on top of a 3-nitride sample, then using a scanning laser or a scanning electron beam, we would induce a spot-like luminescence at the level of 3-nitrides, which would be used in order to have access to the nanoscale optical properties of 2D materials, because then we could have access to the signal of such tiny samples with very high spatial resolution. Note that 3-nitrides have already been used in order to probe the optical properties of cadmium selenide nanocrystals deposited on top, induced by first-order resonance energy transfer. The idea regarding the applications could be the realization of novel generations of micro LED displays mixing 3-nitrides and 2D materials to have a full RGB solution. So the idea of this project would deal with the characterization of near-surface 3-nitride quantum wells with different surface barrier thicknesses. Indeed, the distance between the quantum well and the surface is critical in terms of optical coupling with the nanoflake that will be deposited on top. So here, the idea would be to consider GaN quantum wells embedded in AlGaN barriers, with the top barrier having a thickness of 15, 1, or 0 nanometers. You would have to simulate and design the appropriate 3-nitride quantum well properties by making use of the next nano software that is available in our laboratory. Then you would carry on with experiments, optical spectroscopy of the quantum wells as a function of laser power and temperature. This would be followed by the data analysis in order to quantify the weight of surface recombination on near-surface quantum wells. This is very much important because for other families of semiconductors, such as gallium arsenide, we know that the presence of surface states can have a very strong impact on the quantum efficiency of those nanostructures, and this would have a deep impact on the optical coupling between the 3-nitride quantum well and the 2D material nanoflake. So the keywords for this project are simulation and design, optical spectroscopy, and the physics of surface recombination. So this project is called near-surf quantum wells. The next project deals with the investigation of single photon emission originating from quantum nanostructures up to room temperature. Recently, we reported on single photon emission from gallium nitride dots embedded in an aluminum nitride matrix up to room temperature. And for such an entity, we could demonstrate a bright photon emission a fast emission lifetime on the order of a few nanoseconds, as well as excellent single photon emission features. So in order to quantify whether an emitter is behaving as a single photon emitter, we measure the value of the second order correlation function that should be as close to 0 as possible. At cryogenic temperature, we measured values for the G2 function of 0.05, while at room temperature, it amounted to 0.17. So this type of properties is very promising for testing quantum key distribution using true single photon emitters instead of attenuated laser sources. However, here, those emitters, they are operating in the deep UV range around 4 eV. So it would be much more convenient to have access to single photon emitters operating at telecom wavelength in order to be compatible with optical fibers. And that's actually what can be achieved by probing quantum defects present in bulk gallium nitride samples. So by quantum defects here, we mean defects such as vacancies. So here we can see the case of a missing atom in hexagonal boron nitride. And in our case, the idea would be to probe various samples which have a different doping level, which will induce a change in the formation energy of the defects. And by monitoring the change in the properties of those defects, we could have access to their charge states. And the charge state of quantum point defects is a very important input in order to determine what is their atomic configuration, which is not very well known. So this could be used after by theoreticians doing first principles calculations. Similarly, we would do optical measurements in order to determine the three-dimensional orientation of the atomic dipole. And this would be done by performing photoluminescence emission polarization analysis. This would be a second critical input for first principles calculation. And then we would quantify the brightness and the single photon purity of quantum point defects at telecom wavelength. So preliminary results have been reported 4 years ago by a research group at the University of Singapore, but the idea here would be to be much more quantitative in order to assess the quality of those emitters. So the keywords here are optical spectroscopy, single photon emitters, telecom, quantum science, and technology. And the name for this physics project is QPD at Telecom. Now, the last two projects are dealing with NV centers embedded in diamond samples. The first one would deal with the investigation of the entanglement taking place between two distant qubits using quantum thermodynamics. So this project is based on a theory paper that was published 2 years ago by colleagues at the University of Geneva, where they investigated the possibility to generate entanglement between two distant qubits coupled to two distinct quantum thermal reservoirs. In our case, the idea would consist in considering NV centers that would be our quantum bits, more precisely the NV center's electron spin. Regarding the thermal bath, the cold bath would be the result of the dynamical nuclear polarization of carbon-13 atoms, which would exhibit an effective temperature on the order of a few millikelvins, while the hot bath would be at room temperature and would be the result of the slow diffusion process of the polarization. Then the couplings which are involved in this problem are those occurring between the qubits. So the magnitude of the coupling would range between a few kilohertz and a megahertz, depending on the distance between the bits. It is mediated by dipole-dipole interaction, and then you also have the coupling between the qubits and the bath, which is on the order of a few hundreds of kilohertz, which is mediated by cross-relaxation at the ground state level. So the paper is also in preparation regarding the theory adapted to NV centers. And here, the idea would be to perform the experimental demonstration. The keywords here are entanglement, qubits, NV centers, and quantum thermodynamics. This physics project is entitled Spin Diamond 1, and the final project would deal with the entanglement of 1015 qubits by interrupting superradiance. So the idea here would be to prepare the spins of NV centers embedded in diamond samples by making use of a suitable optical pumping technique. And then here we have built an example by considering 6 spins. You have the block sphere here. Here you have all the spins which are initially prepared in the up state, and by inducing superradiance, then all the spins will relax to the down position one by one. So you will induce a superradiant decay, and when having this decay, you expect to have a maximal entanglement when half of the spins are down. So the idea here would be to conduct an experiment where you would interrupt the superradiance while it occurs, and in order to do that, you would embed your diamond sample within a microwave resonator to be faster than the decoherence process. So it would involve notions of cavity quantum electrodynamics. And on the theory side, we would like to determine whether this system would be suitable for quantum sensing. Indeed, when the system is exhibiting its maximum entanglement, it could be useful in order to beat the standard quantum limit, and also the quantum metrology applications which can be foreseen are interesting when considering the maximum value that can be taken by quantum Fisher information. So here, the keywords are entanglement, superradiance, and cavity QED. The physics project is entitled Spin Diamond 2. And to finish with that, so if you are interested in the near surface quantum well project, you can get in touch with Professor Nicolas Grandjean. If you are interested in the properties of quantum point defects acting as single photon emitters up to room temperature, you can get in touch with myself. And for the spin properties of NV centers in diamond, get in touch with Dr. Mayol Chipo. Thank you for your attention.